In this video 22b, we introduce quantitative models of state changes. First, we introduce an energy landscape for a state change. We talked about energy landscapes when we looked at the spring constants of bonds and how they led to material properties. And we also talked about the energy of a worm-like chain and how that led to the force. In each of these cases, we had a single low energy conformation and we were just moving it along a single well. But now we consider an energy landscape where we have two states, that is, a folded and unfolded, or two allosteric states, etc. So we see this here, that we have two dips, two low energy conformations in this energy landscape here. To set up these models, we're going to use the energy, the Gibbs free energy G. This is the same idea as a U that we used before, just using the G to remind us that the Gibbs free energy is the enthalpy minus the temperature times the entropy. And we'll also now refer to the extension X, and we have a subscript in both of these to talk about whether it's of state 1 with G sub 1 and X sub 1, or of state 2 with G sub 2 and X sub 2. So these extensions are the end-to-end length of the fiber in state I. So this was like the R root mean squared or the R naught when the fiber bridges crosslinks in a material, etc. This is the same concept we considered before. And we're especially interested in here in delta G, which is this difference here of G2 minus G1, that difference in energy, how much greater the energy of state 2 is. And similarly, delta X is the difference in length between these two states. We use statistical mechanics to predict how these molecules will behave. You might recall a partition function that's the sum for all of the states of the exponent of the negative energy of that state divided by thermal energy, although you are likely used to be considering the energy of a mole and then considering RT, the gas constant. So this is the thermal energy of a mole. This is identical. You're just multiplying both energy and the gas constant by Avogadro's number to get what you've seen before is an energy there. But now we have this at the molecular level because we're really focused on single molecules. It's just easier to represent it this way and think about it this way. So our probability by this partition function of a molecule being in state I is 1 over the partition function times the same exponent we have up here, but of this state. So it's really is this thing here that we refer to as a Boltzmann factor, this divided by the sum of all of these for all of the states. Now, if we want to compare two probabilities, that is, we consider just two states, then the 1 over z will cancel out. So we'll define the equilibrium constant as the relative probability of being in state 2 divided by state 1. And as we said, these each have a 1 over z, but those cancel each other. So it's just the ratio of these exponents to the minus energy divided by thermal energy. And a ratio of exponents is the top. So that's the minus g minus the bottom, minus a minus g1 is a plus g1. And then we already defined g2 minus g1 as delta g, and so that reintroduces a negative here since this is g1 minus g2. And we have this value for K equilibrium. That is, the equilibrium constant between the two depends on the difference, the ratio of the difference in energy between the two divided by thermal energy. So we have now these three concepts. We have K equilibrium, the probability of being in the two states, and delta G. And let's just revisit this so we have a better understanding of these. If the two states are equal in energy, G1 equals G2, then delta G is 0. That was the difference between the two states. So now P1 and P2 are identical because G1 and G2 are identical. And if they're identical, the K equilibrium is the ratio of these two must be 1. That is, either way we look at this, the molecule is equally likely to be in either state. And we will use this again later when we talk about the effects of force. Now, by convention, we have defined state 1 as the state that's lower in energy before we apply force. And so we see that drawing here. State 1 is here. Whichever one is longer, state 1 or state 2, doesn't matter, but we'll define the one that's lower in energy as state 1. So because it's lower in energy, by definition, delta G without force is greater than 0. And when state 1 is lower in energy, that means K equilibrium, which is the exponent of negative delta G over KBT. As long as delta G is positive, this is the exponent of a negative number, and so that exponent is less than 1. That is, the K equilibrium is next to less than 1, which means that P2 is less than P1. That is, the molecule is more likely to be in state 1 than in state 2. The probability of state 2 is lower than state 1. So this is just fits the what we know. The lower energy state dominates. And this just shows the math that explains why we say the lower energy state dominates. But degree to which it dominates is determined by this delta G. If it's only on the order of thermal energy, they're fairly similar in frequency, or probability doesn't dominate that much. But when it gets to be many kBt, it's overwhelmingly in state 1. So then we might ask, okay, what if state 2 is longer in length, which is what we show here, on this length scale, state 2 is longer. So this should mean that we can pull the molecule into state 2. So for example, we can unfold a protein. If this is state 1 and this is state 2 unfolded, we should be able to unfold it. And our next question is, how much force is needed to do that? This is the question we will address in the next video.